Okay, so today we're gonna get into spherometers and diopter gauges. Alright, so we're gonna learn how to use a spherometer, and we're gonna use it and measure the radius of the curvature of a lens. And then we're gonna select the spherometer ring base, and I'll show you what that is, because we definitely need to know which base to use when you measure a particular curvature of a lens. Okay, I should say the curvature of a particular lens because the lenses are different. And we also have to know the meaning of the term sagittal height, and we're going to use it. We're going to use it with the ring base information, and we're going to calculate the radius of the curvature of the lens. So these are the things on what we want to do with the spherometer. And here are some examples of lens: your camera lens and your lab lens. Okay, and then of course there's your microscope lens, your choice lens outside to see the different colors, lights. And of course this is your example showing you where your radius of curvature of a lens is. So here you can see going this way, and then you can also see going this way, see the circle. So the radius of curvature for that lens, okay, is this. The radius of curvature for this lens, see that, is this. Okay, and I want to show you we have two different types of lens. And if you have convex lens, look at this curvature, so the radius is going to be around here. And then of course the other side, that's a biconvex. And here you have your concave, biconcave lens right here. Okay, and of course this is your concave and convex lens. Okay, so you now know where the radius of curvature is. Some people love to draw from the center of the circle all the way to the end of the lens curvature. You can do that too, but if you draw like this, it's clearer to see it. Of course, you have to know, the spherometer, it's just a measurement device. So we use it to measure your radius of curvature of spheres or spherical surfaces like this. Okay, see, this is just showing you, and this spherometer is a very ancient vintage one. Of course we have a better spherometer than that now, and you're gonna have so when we measure the spherical lens, right, you can be able to tell the power of that lens. So very important. Lens, we use them in your glasses. So the power of your lens is very important for your eyesight. When you look at this equipment, spherometer, you're gonna have a base, and that's your calibrated base. And then of course you're gonna have a dial gauge, because you are measuring the depth, right? The depth of something. Okay, so that's what a spherometer is. You have your dial gauge, you're gonna have a base, and you're gonna measure anything that is sphere, And of course lens is an example, because that's what we're gonna use in the lab to measure by using this device. So spherometer is just like your dial gauge. We already use the dial gauge in the lab. And so basically it's for measuring the depth. So, we can also call spherometer as a depth gauge. But this is a very old type of spherometer, your classic or vintage spherometer. So this type of spherometer is going to sit on your object that you want to measure, like that, of course. And you can see the legs of this spherometer sitting on that object that you want to measure. And here you can see the central screw, okay? And here this is your circular scale. You see all the numbers here, yes, on the surface of the scale. And it works like your micrometer, yeah, your thimble. So that's your circular scale. And of course, this screw is, you can go up and down, yeah? And you can lower it all the way, yeah? As soon as the tip of this center screw touches the surface of this spherical object, then you're going to stop it, okay? So because we need to read the measurement. Then we will read this vertical scale and then this circular scale to do the final measurement reading. So when you carefully look at the three legs here, yeah, and then the center screw, see that? So the center screw, the tip of that center screw is higher than the tip of the three legs, yeah, of your spirometer. And of course, you have two different scales right here, your vertical one and your circular one, so you definitely need to combine, yeah, like your micrometer readings to get the final readings. And here is your vertical ones, yeah. So this is your 0. So everything below is going to give you the reading for the concave surfaces, and everything above that 0, the vertical 0, is going to give the reading for your convex surfaces. Okay. Then we'll get into sagittal height, which is important for you to know in spirometer reading. So when you take a look at it, you can see this little height. See this one right there, H for height. Okay, so that's a look at this at the tip of this center screw, and then here is the tip of the three legs. Okay, one of the three legs, and of course you're gonna measure from here all the way to here, and this little height is called your sagittal height. And we give positive for convex, okay, and then we give the negative for the concave lens because we're going with this vertical, okay, measurement, because everything below the 0, okay, is for concave, so therefore negative for concave and positive for convex, because everything above that 0, yeah. So anyways, so that's they are relatively corresponding, yeah. The height is from here to here, again the tip of the leg, one of the legs, and then the tip of the center screw, yeah. So the height from here to here, which is the distance between, okay, this point and all the way to that point, and that's little height is called the sagittal height. Then of course we're gonna go straight into the mathematics, yeah. So you can be able to see, because your radius of curvature is from here, yeah. When you look at this very carefully, you're gonna see this, yeah, spherical, your curvature, we call it curve, yeah. It is a curve, so every curve has a radius, yeah, because the entire thing is a circle anyway. So here is the center, yeah, of your curvature, so therefore from the center all the way to, yeah, the surface of your curve or curvature is going to be your r, yeah, which is your radius of your curvature. So here, since the tip is right here, it's a little bit difficult, yeah, for you to be able to see it in a 3D kind of drawing. So if you take a look at it from here, the center point is there, and when you go right there, yeah, and you can see this curvature right there, so definitely we can get the radius of curvature, yeah, the full radius of curvature at this location, okay, of this object, which is your spherical object, and of course your measurement device, your spirometer. Of course, mathematically, and here is your sagittal height, which is really important, yeah, because you need it, because from that sagittal height and the diameter, yeah, of that base circle, we can calculate the radius of curvature of the spherical surface. So when we look at this equation very carefully, you can be able to see, yeah, the radius of curvature is in little r, and then your height, which is this little guy, and that's your saturated height, and then your d is your diameter, yeah, the diameter of your base circle, and the base circle is right there, okay? So the diameter of your base circle. So when you look at the base circle, your circle got to, okay, touch all the tips of your three legs, okay, of your spherometer device, yeah. So here's the first tip, the second leg is here, second tip, and then the third leg is right there, and the third tip. See, like how we draw this circle, and that's diameter, yeah. So your d is right there, and the height, which is your saturated height, and then from there we can be able to calculate radius of curvature in that way, because if you get this and this, you can be able to get this, yes, because you can be able to calculate r by using this equation, okay? So if you look at it very carefully, and we'll have to go back to the mathematics, yeah, your geometry. So when you look at it from here to here is an r, yeah, because this is center, and that is this spherical surface, okay, curvature. So therefore that's your r. So if you go, yes, from here, you can be able to say that, okay, the distance from here to here, yes, you can take h out of r, because you're going to get the same r if you go from the center to the to this, okay, point, which is the end of this little screw point. It's still on this curvature, so therefore it still is your radius, okay, radius of curvature. And that minus the h is going to give you from here, yeah, the center of that center of your base circle, yeah, and then to the midpoint of your sphere. So that is r minus h, okay? So that's where we get the distance from the center of the curvature to the center of the base circle is r minus h. Okay, and the rest of them is easy because it is forming here as a right triangle, because the 90 degree is right here for you, okay? So, and that's your base, which is d, your hypotenuse is your r, and then r minus h, okay, is your adjacent. So this is actually radius, okay, but there's the center, and then of course the end of this circle, base circle. The diameter is from here all the way to the other end, yeah, crossing the center. Don't confuse just because this picture is using d as your diameter, yeah. D here actually refers to the radius. The diameter is going to be from here all the way to the end of here, crossing the center, yeah. And these little things, students get confused, of course. We don't use r here, so you don't want to get confusion with this radius for the bigger, okay, sphere, because you're dealing with two different circle. One is a sphere and the other one is a base circle, yeah, connecting the three tips of the three legs. So be careful, okay? So when you take a look at it, and this is your Pythagoras theorem, yeah, your hypotenuse square is equal to the adjacent, yeah, this from here to here is your adjacent side square, and then plus the base, yeah, square of that 90 degree triangle, yeah. So if you look at it, let me show you. So here I'll show you how to calculate to review your mathematics, yeah. So this is your Pythagorean theorem, and then of course you expanded the square, yes, into the equations. Then we simplify everything, yes, and then we're gonna take r out of that equation. Okay, simplification just moving sides, yeah, from here to that side, and then all the square, yeah, you will, so from here to here you can cancel, yeah, r. So now we have that three terms left, okay. and then we're gonna move this, yes, to that side. See that? So now minus 2RH is now moved to that side, so you have a plus 2RH, and then you have this on this side. And then of course we're gonna move 2H to the other side, your algebra, yeah? So therefore we're left with R, and with this equation, yeah, so your final formula is going to be that, okay, which is this guy right here, okay? So when you take a look at this, and don't take it like D is for diameter, it isn't. D in this example, as shown in this picture, is radius, okay? So anyways, so that's how you get your equation, okay, from your spirometer, trying to get this radius or curvature that you are trying to measure, yeah, this sphere. So this one is your 3D model of the dial gauge right there. Then it has a ring base. See, it is just a little assembly because you're using the ring base and the dial gauge, so it you can mount it, okay, on a lens. So we have two different types of lens. So one is a concave and the other one is a convex. Yeah. So for when you look at this ring base, see, you have a knife edge, yeah, perimeter right there, and this is the one that's going to sit on your lens, yeah. So the lens can pushes on this dial gauge system, so you can get the measurement. So your convex lens, they can push the stem, right, this stem further than your concave lens, because concave is kind of like a going, like I have to show you on this picture again. So here, yeah, so your concave is like this. So when the stem, okay, tip is gonna touch this surface, and it's gonna go down, yeah, further down. And then of course the convex is kind of like that. So the tip is gonna push up, yeah. So that's what we're talking about here, yeah. So concave, and then your convex like this, okay. So like this, okay, your convex is like that, and then of course your concave, we can change this color here. Your concave and the convex, yeah, concave is like that, and then convex is like this. So if you have like a convex, so this is going to push up, and then if you have a concave lens, it's going to go down, yeah. So that's what we're talking about here, yeah. So of course you can also take a look at this and imagine like this is the tip of that stem, yeah. Okay, so this is another example of your spirometer, and you can see this is a metric, yeah. By look at this, okay, and that's your smallest unit, okay, is given to you in, all right, millimeters. So therefore you know that that is a metric dial gauge, okay. Of course, then we're gonna stick that, okay, dial gauge into this base, yeah, base ring. And so by doing that, we're setting up a spirometer, yeah. And then of course you clamp it so you get more stability, and the gauge is going to now attach, right, to the base, okay, in a very stable way, yeah. And then you're gonna have your spirometer ring base right here. It is necessary because you will have to support this, yeah, dial gauge, and then of course our spheres that you want to measure is going to be right under, okay, this base ring. Now we're going to tilt it so you can see, yeah, under the base. So now we have this dial gauge, okay, stem is going to come straight in to that base, and this is your base right here, yeah. So that's your position ground. Ring base is very important because it stabilizes this, okay, measurement device, so you can get an accurate measurement of the sphere that you are measuring. And so when you look at this ring base, it has two sharp knife edges, okay? So this is your inner knife edge, and this one is your outer knife edge. Since they're circles, you have two diameters, from the center to the first inner knife edge, from the center to the second outer knife edge, okay? So don't forget that you have two diameters right in there. Then we're gonna carefully examine the base, and you have your clamp right there, where you are gonna set your dial gauge right in there, and then your inner knife edge, and then your outer knife edge, okay? Knife is just a term that you use, but they can be as sharp like a knife, but it's not that sharp, by the way. And that's your underside of your ring base. We have, of course, different ring bases. Is because you have different sizes of lens. So larger bases is going to give you more accurate readings, like this, and you're going to use the largest base you can for each lens you measure, okay? So you don't get an idea of how to set up a spherometer by using the dial gauge, okay, with the base. Okay, so here are two diagrams. One is for the convex lens, how to measure it. The other one is for your concave lens, okay, how to measure it by using this spherometer. So for convex lens, of course, set up our spherometer system by using this dial gauge, and then a base, so the base got to touch up this convex lens like this, okay? So you have your contact point here, and then another contact point right there, okay? So your from here all the way to here, and see how the concave lens shape, okay, is different from this concave lens, all right? Convex lens shapes is different from this concave lens shape, okay? Of course, from here to here is your inner diameter, because that is your inner knife edge, and this is your outer knife edge. Of course, we are drawing the front view, so therefore you can see the circle from the inner base of this spherometer system. Okay, so the dial gauge reading, since we are measuring the convex lens, your stem is going to push up, so therefore it would be positive, okay? And for your concave lens, it would be negative, because see, the stem's got to go down to touch the surface of your concave lens, okay? So for concave lens, we're dealing with the outer knife edge, so the contact point is right here, and the contact point is right there, so therefore we're dealing with the outer diameter of the base, okay? So this is your dial gauge reading of your concave lens, which is negative. This is your dial gauge reading of your convex lens, which is positive. Inner ring diameter, okay? This side is outer ring diameter for your concave, inner ring diameter for your convex. Why? Because of the shape of the lens, and how they touch, okay? The contact points, look at that, of the knife edges. So convex lens can touch only the inner knife edge, and the concave lens can touch only the outer knife edge. Alright, so make sure that you know how to record the inner ring diameter for the convex and the outer ring diameter for your concave lens, okay? And you gotta make sure to record the inner outer diameter for all bases that you use, otherwise you can't be able to get the correct reading. Then when you have to deal with large lenses, okay, so for large convex lens, the height, look at that, the height of the lens is it's going to increase, so it's going to push the stem up, so therefore you're going to have to choose a short okay stem to measure the large convex lens. And for large concave lens, the stem gonna go all the way down, yeah. So therefore you're gonna need a longer, yeah. So a longer stem for the larger concave lens to measure, yeah. So make sure that you're not choosing the wrong stem length to measure large, okay, large lenses. Shorter stem for large convex lens, longer stem you need to choose for large concave lens. Okay, so here are your dial gauge, your stem here, extensions, because you need to play with that. Depends on the size of your lenses, yeah, concave or convex lenses, because they're different and you will be given a different lenses to measure. So therefore you have to deal with the different extensions, yeah, of your dial gauges. Of course, you have a different screw, yeah, on the stem extensions, because you can use them to adjust the stem length for different sizes of your convex and concave lens. Okay, so how we're gonna do the measurement? So first, you have to do your zeroing as usual on your dial gauge. We will be using a glass plate, a straight, okay, surface like that, to get our zero. So before we measure the lens, yeah, you have to do the zeroing. So make sure when you record your zero, you're going to include this a little dial right in there. Yeah, you have a two scale right there, the bigger dial and then the smaller dial right there. So make sure that you record the zero reading including that small dial. And then we do the same thing, but we're going to swap it, yeah? And you're going to put your, in this case, in this example, you're going to start with your convex lens. And the first thing that you're going to get is the distance from the center of your socle, yeah, to the tip of that stem, which is your sagittal height. Since we're dealing with the convex lens, your reading is going to be positive. Of course, since you are zeroing with a flat surface, when you swap it to your convex lens, yeah, your stem is going to go up, yeah. It's meaning like it will be pushed up. Since the convex lens is going to push up, your reading is going to be positive. So you now understand that your reading is zero, and then when the lens, in case of the convex, is going to push the stem up, so therefore it's going to go over the zero, so that's your positive reading, yeah. So we're going to take a look at it with the real dial gauge instead of the diagram, and zeroing on a glass plate. This is your flat, okay? You're calibrated for the zeroing, and we see the zeros right there. Okay, we have a little bit of the small dial, okay, right here, and the absolute reading, you have 1 and then you have 2, so therefore 2.00 millimeter, yeah. Your larger pointer on 0 and the small pointer is on 2 is going to set you at 2.00 millimeter for this zeroing, okay, setup. Now we're going to put this a convex in, so the convex lens is going to raise the stem up, yeah, so therefore our reading is going to change in your dial gauge. So how much has it changed? It's going to move up about 80 marks. So start out with 0 and go ding, 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 all the way in 80 and stop. And then a small dial is going to show you about 4, yeah, millimeter, because it has to move about 4 whole marks to the positive side. Since your larger dial moves this direction, yeah, from the 0, so it's going that way, so that is your clockwise. So therefore the little dial is going to go counterclockwise from 2, yeah, so there's a 1 and then 2 and then 3, 4 whole millimeter has been moved. So that's your 4, and then you have your from 4 to this much is that, okay, so that's about 80, so you have like a 4.80 millimeters, okay, so that is your sagittal height for this convex lens. We're going to do the same thing for the concave lens. We're going to start out with the glass plate and we'll do the zeroing, yeah. So when you zero your concave lens on the glass plate, you have to have, again, your plunger is going to extend it outward, yeah, because look at that, yeah. So here's a stem and you gauge it for 0 on a flat surface, and then now we are using a concave lens, so the stem is going to go down, yeah, downwards, so furthermore. So therefore you're going to get a negative readings, you know, compared to the 0 of your glass plate. And we're going to do the same thing coming into here. Take a look at this concave, okay, lens right here. I'm going to set this spirometer system with the gauge, dial gauge and a base on it, and your stem is going to go all the way down. Yeah. We assume that we're using the same zeroing as in here. Yeah. So when you look at here, of course, your 0 is right there. Okay, and you would definitely make sure that you also read the small dial. Yeah. So in here it goes about 60, yeah, on this side. So since we're doing the concave line, it go this way: 1, 2, 3, 4, 5, and 6. Okay, and here, since we're going clockwise right there, or counterclockwise right there, your little one is going to go clockwise this way. Okay, so that is about it went from here to about 1 millimeter. We're assuming that we use the same 0, okay, which is this guy. Okay, so that's your starting point, because we're using the same glass plate anyway. Yeah, so you're gonna get 1. Okay, since we're dealing with a concave lens, it's gonna be -1, and we went from here 0 all the way to here about 60, so therefore that's 60, so therefore minus 1.60 millimeter. Yeah, because you need the data sheet for your spirometer rings, and I will provide you this sheet for the LOH, okay, spirometer rings. I'm going to upload that for you, a PDF for you, and you can print that out, or I will print that out for you. Yes, because you need this data, for your spirometer ring. So when we look at it very large, okay, you can be able to see the spirometer, your gauge, dial gauge, and then your base is here, and of course this is your calculation of how to do it, and you totally understand how to go back and just do a little bit to see. So you can be able to see the ring number right there and the corresponding your D, okay, which is your D1 and D2 measurements are given there for you to use. So your D1 and D2 is for your knife edges diameter, your inner and your outer diameter. Okay, so make sure that you use this sheet. LOH is just a company name, okay, because we're using their spirometer base rings. And again, our spirometer base ring has the knife edges, the outer and inner diameter, so therefore you need to know them. Okay, and that is given to you right here according to the base number right there. So make sure that you use the correct base number and the correct outer and inner and outer diameters. And here I'll make it a little bit bigger so you can be able to see it. So this is your inner diameter, because look at that, it's a 5 millimeter, and that's a little bit bigger, which is 8 millimeter is your outer diameter. And of course for inner diameter it's going to touch the convexes, and your outer diameter is going to touch your concaves, lens. So therefore just written here for the inner as a convex and the outer as a concave lens. So by measuring with the spirometer, you can be able to get your height, which is your saturated height, and this is going to give you the D, which is your convex and concave diameter. Okay, and here is our calculation. Your saturated height, and this one is your concave, and that one is for your convex, your saturated height, and your convex and your concave diameters. So here is your formula for the lens radius of your curvature, and this is your spirometer lens radius of curvature that you can be able to calculate. Okay, so equation, your saturated height, and then your base diameter in this case, of course, and here is the description of this equation. Your D is the diameter of the spirometer ring base from the table, and of course you're going to use your inner diameter, your inner knife edge, for your convex lens, and then you're going to use the outer diameter for your concave lens, and both of this is going to come from that sheet, okay, the LOH spherometer base ring sheet. And then your H is your sagittal height, and of course in this example you're using the metric, so therefore millimeter measure using the spherometer, yeah, and your metric or the dial gauge. And then your R is your lens radius of curvature of the lens in millimeter, okay. But that is what you need to calculate, okay. We can get this from the measurement, we can get that from the measurement, and you have to calculate by using this equation to get your R, which is your radius of curvature. Alright, now we're going to get into how to calculate it. Yes, it's pretty easy since we have already measured. So this is a repeated the very first one that we measure for your convex, okay, example, and we ended up getting 4.80, which is your positive 4.80 millimeters, yeah. And then of course we're going to use that in the equation to get our R, which is the radius of curvature, yeah. So the ring number in this case we have used the number 10, so you're going to go to the sheet, okay, ring base sheet, and then you're going to get your diameter ID, okay. So let's go back to the ring base, your LOH spherometer base sheet, and we're going to go to number 10. So here it is, okay, so number 10, so convex is right over here, and then you're going to get the 60, okay, 3, your unit is millimeter. Don't think like this is inches, no, this is just saying it is the same, yeah, millimeter, so that's the 63. The outer is going to be 71 millimeters. And here we go, yeah, we're going to use the 63 millimeter, yeah. So let's put your D is a 63 for this equation, and your H is 4.8 millimeter from your measurement, your sagittal height, okay. And we're gonna put the sagittal height again, and then we're gonna solve the whole thing. Use your Excel, yeah, and you'll get a 105.76 millimeter. Okay, let me check if his calculation is correct. I'm gonna go open up Excel, and we're gonna put the whole thing into Excel and calculate. Okay. Okay, so we are gonna go equal to, because we're getting into a formula to calculate. So on the very first one, okay, oops, what am I doing? Anyway, so the very first one, I'm just gonna go into here is better for me to start writing. So 4.8, okay, and then divided by 2, and then you have to edit, sorry. And then you've got 63, I think, to the power square, yes. And then divided by, and you have 8, and then times 4.8, I believe, yes. And then of course you can just put it all together, yeah. So we have a 105.7594. So he rounded it to 76. Okay, so 105.76 millimeters. So this is correct. Okay, so in the diagram you can see how we get radius of curvature, yeah, from the center of that lens. Of course, your lens is cut it all right here, but you have the entire full circle, yeah. So therefore, the center of the entire full circle is right there, and then go all the way to the tip of that surface of that lens, and that's going to give you your radius, yeah, of that curve, which is your curvature, and that is 105.76 millimeters. We know that this is a convex lens because the height is, yeah, there's a height. Okay. So let's go into another one, which is your concave. Example, we're going to do the same thing. We're going to use what we have measured, and we got negative 1.6 millimeter, yeah? And our base is still number 10, so therefore that's a 71 millimeter that you get it from your sheet, your LOH spherometer ring base, okay? Number 10 is only 1 millimeter for the outer diameter. We're going to just plug that in, okay? So your sagittal height is minus 1.6. Do not forget your minus, yes, and then your D, your diameter, okay, is going to give you 71 to the power 2, which is your square, and do not forget you get this D from a sheet, okay? And then you plug it in, yeah, and then do your Excel, and it's going to give you 394.63. So let's check this out if we're getting the correct one, and I'm going to go ahead and plug this in. Okay, so now we come to here, and this is our convex, and then this is our concave. Okay, and we are calculating our radius of curvature, which is a little r. Yeah. Okay, so now we are going to go in and do the same thing with before. Yeah. So I think it was negative 1.6. Yeah, and then you've got to divide that by 2. And then you're gonna have 71 to the power squared divided by 8 times negative 1.6. Okay, just make sure that we have all of this bracket. So we get minus 394.628. Okay, we're gonna come here and check. So there's a minus here, yeah, this little tiny minus right there, and then 394.63 rounded off. Okay, so therefore that is correct. So here is your concave lens, and then this is the center of that, okay, circle of that curve, which is your concave curve right there, and then that's the minus of 394.63 millimeters. Okay, and of course don't forget there's a negative sign right there here, yeah, and make sure that you put minus 394.63 millimeters for the radius of curvature for this, okay, concave lens. Now we're going to get into a little bit on this, the effect of your spherometer base diameter, yeah, on displacement and your measurement accuracy, of course. This is a vintage one, yeah. We now we use a dial gauge and a base setup. And this is our result. The very first one that we did, we measure, yeah, we measure the convex lens. We use a base number 10, yeah. So this guy is a number 10. So since we use a base number 10, our diameter is a 63 millimeter coming out from the sheet. And then of course we measure the saturated height, and we got the positive 4.8 millimeter for the convex lens. So therefore the radius of curvature for that convex lens is going to be 105.76. This is rounded millimeter. Now we're going to change the base from number 10 to number 7, yeah. And of course number 7, you go to the sheet and you read it, and you're going to get your diameter is 32 millimeters, okay. Your saturated height, and we measure it with this base, a different base, and you get like 1.22, positive 1.22 millimeter. We're going to plug it in everything, and then we calculate it, and it's going to give you 105.53 millimeter. I'm going to check if this number is right. So I write it down here, yeah, the base 10 is for convex is this, and of course we're in metric, so this is sorry, I shouldn't do this. Okay, and this is your millimeters, yeah. And so let's see how. I'm just gonna check if this calculation is correct before we compare. Alright, so let's see, 1 point positive, so 1.22 divided by 2. And then plus, so we have 32 square, yeah. And then divided by 8 times 1.22. So we get 105.528. And that is correct, yeah, because this is rounded, so 105.053 millimeters. So now you have to compare, yeah. So when you compare by using a larger base for the same convex lens, okay, you get 105.76, yeah, and this is a small base, and you get 105.53. So we gotta, like try to design which one is more accurate or more correct, and why. So here, convex, we are going to, of course, I'm gonna just highlight this yellow. So we are comparing the convex, and this is a base. This base is larger, okay, larger, and this base is smaller, yeah. So this is your base ring. And when we check the radius of curvature, we see that, look at this, yeah, 105.75 is larger, yeah. So larger base ring is going to give you larger R, okay. So I'm just going to give you, it is larger R and smaller R, and you have to decide whether this is more accurate or that is more accurate. Okay, so since we're trying to design, okay, between the two bases, the smaller one better or the larger one better, yeah. And let's see how we are going to determine that. So the very first thing that you have to know is here is your small spherometer base ring, okay, with a smaller diameter, of course, and your dial gauge displacement we measure, yeah. So dial gauge 0, the starting point, and then your end point is your, of course, the height of your lens, yeah. So we're on the convex lens. So from here to here, we call that the displacement, yeah. Using this small base number 7, yeah. And we did the same thing for the larger, yeah, base number 10. So the displacement is from here, starting point, yeah, dial gauge 0, starting point, and then we ended up right here for your the sagittal height is right there. So that displacement is actually bigger, yeah. So the larger ring on a given lens is going to give you a greater deflection, okay, of your dial gauge. So meaning like you're gonna have a larger displacement, okay. So when you look at the displacement with a smaller base, it's going to be less than half that using the larger base. But in both cases, okay, you will have to try to calculate the error. Of course, the error is very important for us because we're using the error to be able to determine our accuracy. Yeah. So the larger error you have, the accuracy of your reading is decreases. So first we're going to calculate our standard error by using the smallest unit of your gauge, and your smallest unit is written here, there, okay, for you, which is 0.0005, yeah, inches. So what you're going to do is divide that, okay, divide it by 2 to get the your standard max error, and you're going to get 0.00025 inches, okay. And the measurement that we just did, the displacement, okay, we calculate the displacement, and let's say that we got for the larger base, the displacement is 0.0225, and a small base, the displacement is 0.0100 inch, okay. So now we are going to put that and calculate the error, yeah. So our standard error is that, so the displacement is this, so we're going to use our error, okay, which is this guy, 0.00025 divided by the displacement, which is 0.0225, to get the error of that, okay. A displacement, and you're going to get a plus or minus 1.11%. We do the same thing. We're going to take our standard max error, 0.00025, divided by, okay, our displacement of this small base number 7. So we get 0.0100. So you're going to get plus or minus 2.50%. We're going to compare the error. So this error is obviously larger than that error because this is only 1.11%. That is a 2.50%. So therefore, the larger okay, base is going to generate a smaller error. So we can summarize that. So you have a larger base and then you have a small base. The small base is actually smaller, so number 7, and this guy is number 10, okay? So more than half the diameter of the larger base. So so what you're doing is you're comparing the base diameter, okay? So when you think about the base and the diameter, you go back to that chart, LOH chart, and you look at the base number 10, and then you're going to look at the base number 7. Since we are, in this case, measuring the convex, you're going to look at the convex column, okay, and then compare that, and this is what we're talking about, more than half the diameter of the larger base. Your smaller base or diameter is, okay? And then, of course, however, the displacement of that gauge is less than half, that of the larger base. The displacement is the one that we calculate by using, okay, by using the sagittary height, it goes up, from the 0, point. So that is your displacement. So when you think about that and you saw that the displacement of that gauge is less than half that of the larger base, okay, which is, I can go back here and show you, we're talking about that, displacement. And this displacement, see, that's like way less than this displacement. Okay, so the error is more than twice that of the larger base, which is this. After we calculate it, this is 2.5, and that is like 1.11. So therefore the error is way more than half. And that is happening because as your ring gets smaller, the displacement of that gauge, okay, is decreasing faster than your diameter. So when you think about the ring number is 7 now from 10, and then when you think about the displacement is this guy, okay, right there, and we compare, of course, both of them, and we found that the ring gets smaller, the displacement of that gauge is decreasing faster and than the diameter of the base, and that's because of the curvature of that lens. So when you take a look at that curvature of the lens, see that? So here is your diameter. The diameter is decreasing. It's because it goes up. Your lens are going higher and higher, so your diameter go. So, and of course, you're also using the base number 7. So base number 10, you're gonna have like a bigger diameter. And then, of course, you're going to have like a larger displacement because the lens, see, you're going up from that base line. And here, your base is small, and then your curvature right here of your lens curvature is right there. So the displacement is smaller. Okay, so that's what we're summarizing everything that we have just done. And then conversely, away from, now we're going to reverse it, so don't go crazy when you reverse it. It's just saying the larger base has a smaller error. And you can also reverse and saying like the small increases in the base diameter, meaning the smaller base is going to cause larger increases in the displacements. So this is just talking about the larger the base is, the smaller the error value, but it is just written in a way, okay? So when you carefully read it, small increases in base diameter, so meaning like the base is larger, so when the base is larger, the error is smaller, so therefore the larger base is more accurate. So here you can be able to see how your spherometer base diameter is increasing in uniform increments. So the rings are uniformly spaced, so horizontally. So this is your bigger ring, and then smaller, 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 and go all the way up. So your a larger base, and then go all the way to the smallest base right here, with of course that much of increment. So each time the base diameter increases, so there's a small diameter, now it increases, diameter is increases, so the vertical displacement, so the vertical displacement is this guy, So the base, and then go all the way to like wherever you want to stop. I want to show you, okay, that again, which is this one, yeah, the vertical displacement. So your base is here, and then to the tip of that, yeah, lens curvature. So your tip of the lens curvature is right there. So if your base is here, then of course you're gonna have, yeah, that displacement changes, yeah. So your lens tip is right there. So the base, yeah, small base, the displacement is only that much. Now your lens tip is right here. Next larger base, your displacement go larger and larger, and so and so. Okay. Okay, so this is just repeating what we have just summarized, okay, right here. But we can go over again. So if you have a lens that you want to measure that lens radius or curvature, then it's better to use a larger ring base. Why? Because it's going to give you a smallest error. Yeah. So why? Because when we measure, yeah, you have a larger deflection because the displacement for the larger base is larger. Yeah. But okay, so we're just summarizing it again or writing it, yeah, what we have all done before. So basically, it's talking about it's better that you use a larger base. Okay, so to choose the largest base you can be able to get in the lab, because it's going to give you the minimum, yeah, measurement error. As you know, the measurement errors are calculated from your maximum standard or maximum or standard error. And that is based on the degree of precision, yeah, on the device that you're using. So the dial gauge of precision, you're going to go to the smallest unit and then divide it by 2 is going to give you your max error, and we're going to use that max error divided, okay, by your displacement is going to give you the errors of that system, yeah, spirometer system. So this is how we designed using the largest base possible is going to give you the smallest error. Yep. So therefore advise you to use the larger base when you do the spirometer system. Okay. Of course, some students is trying to memorize the greater deflection of the dial gauge. It's just talking about that you will get a larger displacement, okay, from the 0 point all the way to the tip of the your lens. Okay, don't forget the tip of the lens. Therefore, this is your convex, okay, lens. For concave, it's going to go down, okay. Displacement is going in reverse direction or negative direction. Okay, so based on that fact, you have to know like which ring, okay, base that you should select in measuring your lens. So the very first one is your convex lens, and then of course we have diameter D for a ring base. Okay, so your lens diameter is 26 millimeters. And it asks you, okay, which ring base number will you select for measuring the sagittal height? The sagittal height again is from the base of that, right, ring all the way to the tip of that lens. Okay, so we want the largest inner diameter that is smaller than 26 millimeters. So your ring number, you're gonna go back to the sheet and then gonna try to find, yeah, 26, and you're gonna choose something, okay, around there, which is your 25 millimeters. So let me go back to the sheet and show you. So this is your sheet, okay, and you can see right there 6, ring number 6, which is your base, yeah, ring base, and see that 25, and you have 32, the next one, 20 is the next one, but ours is a 26 millimeter, okay, so therefore we're going to choose that. So now we're back here, so now you understand why we choose number 6 ring, yeah, to measure this. First, you're given the lens diameter. The lens diameter is 26 millimeters, okay. And when you choose, we're going to look at that lens, given lens diameter, and you're going to choose something that is smaller, you know, the largest inner diameter that is smaller than your lens diameter, and we found, and that is ring number 6, which is 25 millimeter, which is smaller than 26 millimeter, the lens diameter. Okay, so what diameter will you use for the ring base when calculating the radius of the curvature of the lens? Now we're gonna reverse that. Yeah, so the question is asking you what diameter will you use for the ring base. So now we want the ring base diameter, so when calculating the radius of curvature of the lens. So your inner diameter knife edge for the ring number 06, okay, and that is a 25 millimeter. And that gotta be sitting on the lens like that, yeah? So the inner diameter knife edge, the inner diameter of your knife edge, which is the inner diameter of your base, is going to rest on the lens, so that is going to be 25 millimeters, yeah, for the ring diameter in the lens radius calculation. So if you have a confusion here because of the terms and the symbol, you know, and the problem is going to confuse you by using different symbols, yeah, and different terms. It's the same thing, okay? You have your sagital height, you have your diameter, okay, which is actually the inner diameter or outer diameter for the concave, inner for the convex, yeah? It doesn't change whether they use a little d or r or big D or big R or whatever symbol that is, yeah? You just have to go with, do not always take like the radius got to be always R. Okay, the diameter got to be always D. Don't do like that. Okay, it can be anything, any symbol. Yeah, variables can be named any way you want it to be. So therefore, all you have is a radius of curvature is based on the sagittal height, which is sagittal height, which is this guy, and then the inner or outer diameter of your base. That is all you have to understand. Okay, so therefore you're going to use a 25 millimeter, yeah? You're not going to use a lens diameter. Lens diameter is not the base diameter. The base diameter is the one that you will be using in the equation, okay, with the sagittal height. And the sagittal height is the one, yeah, which is the tip, okay, from the base, okay, of that I would say like the ring base, okay, the base of that spirometer system setup, okay. So make sure that you understand the basic or the foundation of the mathematical model, yes, and do not confuse with doesn't matter what terms the problem is using to be able to see that, yeah. So use your intellect to differentiate different symbols and terms. Okay, we have nothing, your radius, which is the curvature or the lens or radius, and then we have the height is a sagittal height, which is the tip of the your lens to the base of that, okay, inner diameter base, and then you have your diameter, which is the inner or outer diameter of that base. That's it. Okay, so make sure don't forget that. And then of course we do the same thing. The lens diameter is D, and that's a 141 millimeter. And then which base are we going to use? We're going to go back to the sheet, okay? And then we're going to look for 100 and around 141, because your base got to be less than that, okay? So now we go back to the sheet. So when you go to 141, we see this, see, 140. So we're going to come back into here, that's 141. So that number is going to be, yes, so when you look at it, it's a 17, yeah? So ring base is going to be, I don't know why they're writing here on 16. So, oh, wait a minute, sorry about that. This is a concave lens. Yeah, sorry, so concave lens on 140, so you're going to have a 16, yeah? So concave lens 140, okay, is less than 141. And the number of that ring is going to be 16. Okay, so sorry about that. I get into the same convex lens. Actually, we're in a concave lens. Yeah. So therefore, the ring number is 16, and that's what we're going to use. Okay. So for the diameter that you need to calculate the radius or curvature, yeah, we are going to use this diameter, which is 140 millimeter. Do I have to show you the equation again? I could do that, yeah. So the second question is asking you this diameter, okay? What is this diameter? Do I use a 141 or 140? You're going to use a 140 because that is the base diameter, okay? And let me go back. Okay, so what I did right here is I put the equation for you, yeah? So you don't go into confusion when you look at it. I'm just asking you what is this diameter, yeah? The spirometer lens radius, and this is your radius of curvature, okay? So this diameter is actually your ring base, okay? So which is your ring numbers 140, and that's the one that you're supposed to be using, okay? Not this. That's just telling you the lens diameter, okay? All right. I of course also put here, yeah, for you next to your the ring base chart right here. Now you're going to do the same thing. Your lens diameter is given 161. Yeah, we have to come up with the ring number. So the selection of your ring base. We're going to go and take a look at the lens first. So your lens is on this side is your convex, and then on this side, okay, you have a concave surfaces. So you have two different surfaces, okay, in your irregular lens right here, yeah. So the very first surface is a convex, so therefore we're going to look at the convex column right here, yeah. And then you have a 161, so therefore that's got to be less than 161, so we have a 18 for the convex, yeah. For the concave lens you have a 17, okay. So that's basically what we're talking about for the convex lens. We're going to use ring number 18, yeah. And of course, you will use a 160 millimeters, yeah, for calculating, yeah, by this diameter. You'll be using 160 millimeters for the concave, okay, surface. We're going to use ring number 17. And then we are going to use the same, which is 160 on this diameter, okay, in this equation. I could copy and paste the equation right here for you too. So I add the equation here for you, so you know that this little d, okay, and that is what the question is asking you. What diameter for the ring base will you use? You're going to use the 160 in here, okay? So make sure don't go into confusion. Make sure which lens that you're dealing with, whether they are your convex lens or your concave lens, okay? And so you can be able to use the column correctly, okay? And when we actually calculate the radius of curvature, this d got to be, okay, the base diameter. Okay. Then we'll get into diopter gauges, okay, which looks a little bit the same as your dial gauge, but when you carefully look at it, they are different, yeah? Alright, so we need to know what diopter gauge is, and we need to know what we use it to measure. Okay, we usually use this to measure the power of a lens. And then we have to understand that a convex lens has a positive power and a concave lens has a negative power, just like in spirometer reading, yeah? And then we gotta know how to calculate the radius of curvature of a lens from the diopter gauge or reading, okay? So these are the things that we're gonna do in this lesson. I'm going to go back a little bit of review, and here's your lens. Your radius of curvature is this guy, yeah, from here, the center of this circle, because this circle is actually the same, yeah, curvature has the same curvature as this lens. And then of course on this side, so we have a convex and convex here. So convex for this radius of curvature, okay, is this r, and that radius of curvature is this r, okay? So if you have like a little higher, yeah, convex or convexity, that we know that the radius of curvature is smaller. Yeah? You have a bigger or larger radius of curvature if you have your convexity is lower, okay? Okay, so on diopter gauges, we use it to measure the lens power, directly, because you can see the scale right here, and that is the diopter, or the power that we measure. So the face of that gauge is your diopters or power again. So what we can do is you can bring your glasses and then we can measure it by using this diopter gauge to know the power of the your reading glasses. Okay, so the weak reading glasses is going to give you like 0.5 to 1.0, and your strong reading glasses is going to give you 2.0 to 3.0. Okay. And of course, when you take a look at this diopter gauge, you're going to see we have two outer pins, okay, and they are fixed, and we have a center pin, okay, and this pin is definitely movable and it can be pushed, okay, and like your dial gauge. Another thing that we can be able to calculate from the diopter measurement or reading, okay, on this gauge is that you can calculate the radius, okay, radius of your lens. Of course, there are several formats, but they all do the same thing, and we're going to take a look at it, okay, one by one. So zeroing the diopter, so these are the two types of your diopter gauges that we have here in our lab. So you're gonna check zero by placing the gauge on a flat, okay, glass or plate, just like we did in a spherometer system, and then your both gauges need to have their zero adjusted. Okay, so here is our zero, and here, okay, the second type is right here, your zero is right there. And don't worry about this because when they take the picture of this, if somebody's holding here, and because of the angle, you can see like it's not on the zero, but actually it's on the zero. It's just the camera angle is taking the picture from this side. So that's why the camera lens is supposed to be 90-degree on it. So that way you can be able to see this hand is going to be on this zero directly. So what we're doing here is the same thing. We are zeroing or adjusting the zero in these gauges. So by adjusting the zero, so how do you do it? So you're gonna turn the center pin, which is this guy, okay? Turn the center pin, and then you're gonna recheck the zero. You're gonna do it again and again until your hand, okay, of the dial gauge is your hand of the diopter gauge is on the zero, okay? So whereas zero on these gauges, zero is a little bit off. Thus, again, it's just because of the camera. Okay, now we're going to take this, right, and we have a negative and a positive diopters. We call it diopters, so that's the units of power. And we're going to put it on a convex lens. So here it's the center pin is right there, and that is going to get in touch with this. And of course, so you're going to pay attention, where is your zero on this gauge. Okay, so when you take a look at it, you're going to see the zeros right up here. Now I'm going to use a little pointer so you can be able to see where the zero is on this gauge, and note that that zero is at the top and not right there. And when that gauge isn't touching anything, the movable pin, which is this guy, okay, so the middle one is a movable pin. So that movable pin is fully extended and it's not reading the zero at all. Then it's gonna it will only read the zero when it is placed on a flat plate. Okay, right now it's not gonna read because it's not touching, okay, a flat surface. It's just we are about to put, okay, the diopter onto the convex lens in this picture, of course. So as you bring this gauge down on the lens, you have to watch, okay, how far the needle rotates past that zero. Okay, so this is your needle, and how far that needle is going to rotate past that zero. So that's what we're reading. So it may make a full revolution past a zero on higher power lenses with high curvature. Meaning, like if you have a very high power lens that you're measuring, it's gonna go just past that zero and go all the way. So that's what it's talking about. Now we're in contact with the convex lens and how this little middle, okay, you see that the center pin is being pushed upward. Yeah, so because of the convex lens curvature is going up. Yeah, so now you can see, yeah, from 0 is going to go past the 0 to the positive side, because when the diopter gauge is landing on a flat surface, the pen is going to be at 0. Yeah, so now the flat surface is going to higher because of the convex lens curvatures go up, is going to go to the positive side. Okay, so that's this diagram is showing you how this hand moves from 0 to the positive side. Okay, that much, of course, 0 to 5. So that's altogether you have a +5 diopters. Yeah, so that's the power of this lens. So this lens surface power is a plus 5.0 diopters. Okay, that's pretty high power. So here is your glass plate flat surface, and you can see, you know, how we zero this. So your zero is on a flat glass plate. We're going to adjust the zero by turning the middle pin, which is this guy, okay? And then we're going to swap it, of course, to do the same thing like as in gauges, yeah? And you're going to swap it from the glass plate to the convex lens, and it will go down that way, yeah? So the pointer is going to move to the positive direction relative to that 0, and the reading is positive for the convex lens. Okay, why? Because it pushes, you know, this little middle movable pin or your plunger in or upwards, and then your concave lens is going down. So therefore, from this, you know, surface, it will go to the negative direction. So you're gonna see the hand, it moves to the negative direction that much. Okay, so now we are reading the negative, okay, values because of this concave lens is going down, okay, from the flat surface. So the pointer is moving to the counterclockwise direction, and this guy is a clockwise direction. Okay, I think you get it. Okay, so the very first example was with the convex lens, and at that time we get a +5, right, diopters from this reading in this example, and we're going to convert that lens radius curvature, and we're going to use that in this, okay, formula. So in this formula for this level, we're using a different formula, okay, so that's a 530 divided by P, so that's the lens or radius R in millimeters, okay. So while we're having this 530 divided by power, yeah, which is a P, which we measure is +5 diopters. So why we're using this equation is because of the material. Yeah. So if your material is a, you know, for of course for this the optical glass material is a typical one, so therefore we use 530. Yeah? So if this material, this lens is different, then we're going to use according to that. Okay, of course it's going to come from the chart. Okay, and we have different standards, yes, of the materials. So anyways, in this material we're going to use a 530, and that's a typical optical glass for this convex lens. So therefore 530 divided by the power, which is 5. Okay, so therefore your radius of curvature is going to get 106 millimeters. Yeah, and make sure that you don't forget the sign, because our power is a plus, which is here. Yeah, we should put right here as well. So you're going to get like +106 millimeters. Yeah, the radius of curvature by using the diopter gauge, and we can get the radius of curvature without doing a lot of mathematics. Okay. All right. And the next one, your both sides of the reading glass lens. So because if you have like something like this, okay, a concave and then a convex lens, and you have to measure both of the lens. So for the convex side, the reading is, we're going to do the same thing as we did like in here. Okay, first you gauge a 0, and then we're going to put the convex side and then concave side. And after we measure that, we get the convex side reading is a +4.75 diopters. Okay, and then don't forget you have, okay, don't forget that you have a 2 scale, okay, the very big, and then you have another one down here for your power. Yes. And this diopter gauge is a little bit tricky. Yeah, so when you take a look at it, see like where the pin and the 0 is on the same side, not like the one that we just, okay, this is a different type of a diopter gauge. Okay, so just be very, very careful which one is positive direction. So going on this way is a positive direction for this diopter gauge. Okay, because your zero is on the same side as your pins. Okay, so therefore that side is zero and that side is a negative. So in this case, what we got right here is a positive. You go da 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 all the way, and that's a 4. And then down here is about and from here to here is about 75%. Okay, so that's you get 4.75. Yeah. On the concave side, we get that way. So that's a 1, okay, and that's a 2, so therefore -2. And then this is about 25%, okay? So therefore you get -2.25 for the concave lens, okay? So the 25, okay, it comes from the lower scale. So that's a 10, and that's a 20, and then that's a 5, okay? So that's why you get on 25. So make sure that you also read the same thing, okay, here. And then since this is the same lens, even though it has like a concave and a convex surface, okay, on the same lens, you have to combine the power of two surfaces together. So the very first one is 4.75, and the second one is a -2.25. So when you combine it, you get positive 2.50 diopters for this entire lens. Okay. To me, when I actually read this, I got it like 5.25 here, okay? But anyways, I will ask whoever wrote this before. But anyways, you kind of get the idea. I think like somebody who read before me got it a little bit wrong right here, yeah? Because if you make it very, very big, let me go ahead and change this again. So I'll make it a little bit bigger so we can be able to see it, okay? So here is like this 10 or 20, okay? And then of course you're getting that. And that's about 25. So here I see like a 1, 2, 3, 4, 5.25. Okay, so let's go ahead and change this here. So I go ahead and I change this, and I will update your handout for you. So you should get about like 3. So anyway, so you kind of get it. Okay? So some people have issue reading. Maybe they didn't see it or something. I don't know. So anyway, so that's how you read your diopters. Yeah, so let's take a look at another example. And of course, we have to check, okay, if their numbers are correct or not. Another, this lens, we have a convex and then the concave, okay, side, two sides right here. So the very first one that we measure, let's just make sure this is a different, okay, a diopter. Here on this side is positive and that side is a negative. So we have 0 here, and we go all the way to 1, 2, 3, okay, 4, and this is correct. Yeah, so this one has a 4.75, and then this side is we have 1.5. Yeah, so this is correct. So we have a 3.25 for the combined power. All right, the next one is your example problems, and I'm going to show you how to do it, and then of course you're going to have to do the exercise, yeah, by yourself. So the very first one is, oh, where is the 0? Yeah, you have to find that, and then of course you are going to find the radius of curvature, yeah, by using the diopters of power. And you know that the radius of curvature can be calculated from the material, yeah, divided by the power, which is I should give you the equation again. So I added the equation here, so you know that this is where you're gonna plug in your diopters of powers of reading right there. Yeah. So the very first one is this, and you're gonna have to make it big, okay? So here we make it big, and then we read it, and that's going to the negative direction, which is minus right there, and then we went like a 17.5, okay? I don't want you to have a confusion for the zero, okay? You have to make sure that where you're counting from, and that is a 0 point, okay? The zero is right here, yeah? So going on this direction, so therefore you have a 17.5. If you mistakenly measure from here by thinking that is a zero, you're gonna get a bad, okay, reading. Okay, and then you're gonna plug this, okay, in to this equation. So this equation, okay, so 530 divided by your power is your negative, and don't forget the positive and negative signs, so 17.5, and you get the radius of a negative 30.29 millimeters, okay? And then we do the same thing for this guy, and then your zero is right here, and then you go into read, okay? So and go down here, you get a 20, yeah, 7.25. So let's make it bigger. Yeah, so you can be able to see it go that way. Yes, and then this is it's a little bit difficult for us to be able to read it. So anyway, you can see like 7, 8, and then 9, 10, 11, 12, and then 13 here. Yeah, so this actually we're counting, yeah, from this side going this way, and that pass like 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and then of course we take about 25% on here, okay? And you have to make sure that which diopter gauge that you're using, this is different, okay? This diopter gauge is completely different from this guy, yeah? So what is different is, see, like, look at this, okay? And here we're reading either this direction or the other side, okay? Because the lens is not, okay, it's really concave and convex, okay, going this direction and then that direction without doing one revolution, okay. This one is a different, okay, diopter gauge. Is because it has an indication of which direction, yeah, this dial gauge or diopter gauge is going. Yes, so this one is telling you the needle move clockwise from 0, and then the reading, and the convex and concave and the radius. See, the needle move clockwise from 0, okay, for this as well. See that? And this is the reason why we have to come from here all the way to here and not the other way around, okay, because of this little sentence right there. Yeah, and here there is no condition like that, okay. We are reading directly as the needle goes, yeah. So when you read it, the needle goes that way, so we read that. And then when you read this, the needle goes this way, so we read that. Yeah, here is this diopter gauge is different because it said the needle move clockwise from 0, so therefore it got to count clockwise for this, okay, even though you have a tendency that you might want to count from 0, okay, all the way down here like that, okay. All right, so anyways, so plug this in to this equation, your power including the negative signs, and you're going to get like minus 19.45. All right, we do the same thing, and this time, okay, counterclockwise. See the CCW? So counterclockwise is going to go this direction, okay? We're going to read accordingly that. So therefore we get 22.5. And this one, the same thing, counterclockwise going this direction, so we get 12.75, yeah? And then do the same thing, plug it in your power, and then you will get the answers, okay? And we do the same thing here, yeah? Here it doesn't say anything. See, it's a concave lens, and here it said so. The needle move counterclockwise from 0. So therefore, you've got to go counterclockwise from 0 and then plug it in here at 8. Okay, you'll get 66.25. This one doesn't say anything, so therefore, you're going to read as it is. Okay, so it will go a 4.25 from the 0, which is 0, 1, 2, 3, 4, and then 25. Okay, and plug it in and then calculate it, and you get minus 124.71. Yeah, all right. So anyways, that's it for the spherometer and diopter gauges. Yes.